Hi, kids. All right. Excuse me. All right, I'm ready. Hey, sorry. Just clearing my throat because this is going to be fantastic. We're going to learn about single slit interference. So remember, to be successful in physics, you need to be able to draw a picture of what's going on. You need to be able to represent the physics phenomena with math, and then you need to be able to explain in words what's happening. So let's draw a picture of what happens with single slit interference first. So let's say over here, I am going to have my single slit. So there's my single slit. Okay. Now, and then, if I have my light rays coming in this way, okay, remember the width of this slit has to be on the order of the wavelength. Otherwise, you're just not going to get the interference. So this slit has to be pretty small compared to the light, the waves that are coming in. And then let's say over here is the wall, okay, my screen where I'm going to get my interference pattern produced. And remember, okay, that when this happens, you get like this central blob. And a lot of times they call it the central maximum. They actually don't call it, when they talk about single slit, they don't actually call it the zeroth maximum, because not every place in this blob is the path difference 0. Okay, and we'll talk about that. We'll talk about what I mean by that. And then you get this, so it's kind of like really bright in the middle, and then it's less bright here. But then you get a dark spot. And the dark spot is really obvious. So there's a dark spot here. So the dark spot's going to look something like this. There'd be a dark spot here, and then you'd get another bright spot, and then you'd get another dark spot, and then you would get a bright spot, another bright blob here, okay, and then so on. And it's going to get way, way dimmer. So like this by far is the brightest, and then this is the next brightest, and then the next one, if I was to draw the next one, I can't do it on top because I ran out of space, but the next one would be ridiculously, now it'd be the same width as the others, but it would get really, really dim as it goes. Which is why if you're looking at like the brightness pattern for this, it would look something like this, where this middle one is very bright, and then this gets much dimmer, this gets much dimmer, and then this gets much dimmer again. So this would be like if you were graphing, brightness, okay, versus position, okay? So it would get much, much dimmer like that. Okay, so because the dark spots are the ones that are well defined, that's where we're going to go to, okay? So we can't really go to here because, well, it's not so well defined. The dark spots are the parts that are well defined. You're also going to see the bright spots. Some of it is really bright, and some of it's kind of bright, and some of it's not very bright, okay? But you should have already done this and looked at it, so make sure you, if you haven't seen it, go back and look at that interference pattern again, because that's really going to be a big deal, okay? So let's just think about what we're doing. So we're starting here, okay? We are starting in phase, and you might think, well, geez, there's only one source here, and there isn't. We'll get to that in a minute, but let's just jot this down. So remember, we are starting in phase, so our starting condition would look like this, in phase. And then I am ending at one of these dark spots. That means my ending condition is going to be out of phase, so that if I'm starting in phase and ending out of phase, that means my path difference has to be off by a multiple of a wavelength. Or, sorry, I have to be off by a half of a wavelength, okay? So we could write it this way, where then M would be, 1, 3, 5, and so on, okay? But I have to be off by a half a wavelength. Does everybody understand? Hopefully that makes sense why. Because I'm starting in phase, and I'll show you where we're getting our two waves in just a minute. And then I'm ending out of phase because I'm going to my dark spot, okay? So that's important. Keep that in mind. All right. So now let's talk about, well, how do I have different sources? Well, if you remember Huygens' principle, okay, this wave that's coming in, really there's an infinite number of wave sources along there. Remember that each point along the wave acts as a wave source. So really, I have lots of wave sources. Well, if I want to name all of these, here's what we're going to do. So if I call this distance d, like how far apart that slit is, to name all of those spaces, I'm going to talk about this one and this one. Okay, so the one right at the edge and the one right in the middle. Why am I doing that? Because if I go two dots that are always, that would be d over 2 away from each other, well, I could go a dot here, and then I would get a dot right below it, and then a dot right there, and a dot right below it. And that way I could get every single source in between if I take them so that they're a half d over 2 away. Where if I did this one and this one to start, that's only good for that pair. Because that's that pair, there's only one pair that is that far apart. But if I go d over 2, there's an infinite number of pairs that are d over 2 apart as I go from here to here, and then I can hit every single one. Okay? So I am going to go to, I don't care, I have to go to a dark spot. So let's say I want to go to here or here. So if I sketch this in, this is straight across. Okay? If I decide I want to go to this dark spot, so let's go to that dark spot. And I got to draw a straight line. That's supposed to be a straight line. I'll call this L1, and then if I draw another straight line, that's supposed to be a straight line, I'm going to call that L2. And then if you look, okay, the path difference would be that little piece. Okay, let me zoom in. Does everybody see it? So the path difference where this is a right angle, the path difference, and again, this is only true as long as this distance here is pretty far, okay? But that would be my delta L, which would be L1 minus L2, which we already said that has to be equal to this, because I'm starting in phase and ending out of phase. Well, if you take a look, this distance is d over 2. And then if you do your trig stuff, remember, and again, it's not perfect, but it's pretty darn close as far as the similar triangles go. It's good enough for our purposes. This angle and that angle are going to be the same. So then, hey, guess what? This is going to be d over 2 sine theta. So delta L is also going to be equal to d over 2 sine theta, which equals m lambda over 2, which, hey, guess what? I get the same equation. Which is why, if you look on your equation sheet, it's just d sine theta equals m lambda, okay? Because, okay, it's the same equation, it's just the difference, and this is a big important difference. Let me zoom back out. Where when you did double slit interference or you do diffraction gratings, you're always going to a bright spot because they're well defined. Here, you're starting in phase, ending out of phase. Okay, so you're going to the dark spots. So, a couple other things that I want to mention to you, okay, and hopefully it makes sense. So this is where you'd be off by a half a wavelength. This would be a half a wavelength. This dark spot would be you're off by 1.5 wavelengths. Okay, and then this dark spot down here would be you're off by 2.5 wavelengths, and so on, just like we did before. But it should make sense. A couple things. A lot of times when you're talking about single slit interference, maybe they'll ask you to solve for how wide this is. Okay, well, if you know this distance, actually let me draw it in a different color just so it's easy to see. I'm going to draw this red triangle in. okay, where I know that theta. Does everybody see, if I know this L, which usually they give you that to you, the slit is this far away from the wall or the screen, and I know that theta, I can use my mad trig powers to solve for this distance. And I'm going to call this distance W over 2, where W is going to be that whole thing. Does everybody see that? Well, if you solve for this, which you can, all you got to do is multiply it by 2, and now you have the central, the width of the central maximum. And then at the same token, does everybody see why this one is half the width of this one? Okay, because again, the same idea, goes for there. And then the last thing I just want to note, because you might think, well, geez, the reason this is called the central maximum, not the zeroth maximum, is that there's probably a point down here where the path difference for the two waves, it's not 0. Do you see what I'm saying? So, and the reason that it's a little bit bright is that I'm not getting perfect constructive interference there, but I'm getting some constructive interference. And that's, again, why we don't go to the maximum with a single slit. We go to the dark spots. Okay? All right. With that, you should be able to solve the problems. Remember, understand, understand, understand. Don't memorize. All right. Bye, kids.